Okay, thank you very much. Hello, everyone. My name is Zhang, first-year master's student in Beijing Normal University in China. Firstly, I'd like to thank the organizing committee for giving me this opportunity to talk. And my talk is about the granulation of real supergiant stars. And my collaborators, also my supervisors, are Professor Biwei Jiang and Dr. Yi Ren. We have known a lot about the real supergiant stars through this morning. They are almost the brightest and coolest stars in our universe with a significant mass loss at 10 to the minus 6 to 10 to the minus 4 solar masses per year. The granulation is basically the movement of convection cells near the stellar surface with hot and bright in the middle and dark and cool at the edges. Because convection is much more popular in the supergiant stars, so the granulation is much more expected. Schwarzschild predicted that the surface of red supergiant stars should be dominated by convection cells, and this was proved by the simulations or observations of Betelgeuse shown here. Here is a simulation of the Betelgeuse by Freytag et al. And Kubel team. Granulation can enhance mass loss, and so it's important for us to understand the red supergiant stars. But Betelgeuse is the only case for us to study because other red supergiant stars are too distant to be directly imaging. Fortunately, the convection cells on their surface are large enough to significantly affect their latter variation, so we are able to indirectly study them through the light curves. The light curves of red supergiant stars can be divided into three types: the irregular variations, the long secondary period, and the semi-regular variables. The semi-regular variations usually have a light curves like this, like surface. There's a periodic light curves. So they also follows a period luminosity relation shown here by Zhang et al. Red supergiant stars are positing in fundamental or first order tone mode. Because they are much brighter than surface, they may be a better standard candle to measure a larger distance. The long secondary period usually have a period more than 1,000 days or even more, and its mechanism is still unknown. This talk will mainly focus on the irregular variation shown here, and we believe that they are mainly caused by the granulation. Case et al. And Yang and Zhang both noticed the red noise in the power spectral density of light curves or supergiant stars. The red noise means the power spectral density decreases with the increasing frequency. So it suggests that the irregular variation of red supergiants may come from stochastic process, that is convection. So a basic way is to directly fit in their PSD, and this was first modeled in the Sun by Harvey. He used a Lorentzian profile like this with two key parameters, the amplitude sigma and timescale tau. Since then, some modified Harvey functions are used to fit the background of the PSD, especially in the field of astral seismology. For example, the exponent in the denominator can be replaced with a free parameter alpha, or multiple Harvey functions can be summed together. This plot shows an example of a PSD of red giant stars and the fittings with several Harvey-like functions. But there are several issues in calculating the PSD. The non-uniform sampling and finite duration will cause unpredictable window effects, and the ground-based observations will introduce some false periodicity because the telescope can only observe at a certain season of a year. So the parameter estimation from PSD will be biased. When the plots give an example that signal shown here, after applying a non-uniform window effect, and their observed PSD will contain a lot of noise, making the expected peak not prominent. So directly performing a Fourier transform to the light curves and then fitting the PSD is not reliable. Ren and Jiang use a continuous time autoregressive moving average model, that is a comma model, to study the granulation. The comma model is basically the solution to the stochastic differential equation, and this plot shows an example to use comma to model the light curves of red supergiant stars. Then we can get its corresponding power spectral density, and it's called the posterior PSD, shown here in the blue line. And then they use a Harvey-like function to fit the posterior PSD and to get the granulation parameters. It can be seen from this figure that the posterior PSD shows the red noise features and traces the background well. They also analyze the relation between the granulation parameters and stellar parameters and find a close linear correlation, and that is the scaling relations. That is because the effective temperature tau is proportional to the pressure scale height over sound speed, and the amplitude sigma is proportional to the sound speed over the square root of the numbers of the granules on the stellar surface n. And these physical quantities are also related to the stellar parameters, and that's why the scaling relation holds. They also compare their results with the red giant stars from the asteroid seismology analysis shown in the gray dots. However, their work only focused on the bright red supergiant stars because their faintest stars is still over 10,000 or 20,000 solar luminosities. So this motivated them to create a more complete sample of red supergiant stars. It seems really easy to select red supergiant stars in the color magnitude diagram, but they are highly contaminated by the foreground stars, mainly the red dwarfs in our Milky Way. So Ren et al. Proposed a G-H, H-K diagram to distinguish the giant and supergiant stars from the dwarf stars, mainly because the H-band is sensitive to the stellar surface gravity. And then they can identify the red supergiant populations in the color magnitude diagram and obtain the nearly complete sample for 14 galaxies in our local group galaxies. We also obtained the light curves. The V and G band light curves are from the ASAS-SN, and I band light curves are from OGLE. It's important to note that the OGLE photometry was saturated for the bright stars, so it only includes the faint one, and the ASAS-SN light curves didn't have enough depth to detect the faint source, so it only includes the bright one. This figure shows two examples of light curves in these three bands, and the number of the light curves we collected are shown here in this table. We use a Gaussian process regression to study the granulation and to directly model the light curves to avoid several issues mentioned before with the PSD. The mathematical principle of Gaussian process is that each point in the time series can be described as a Gaussian distribution with a specific mean and variance. And this is defined by their kernel function. We use a Python package Celery 2 to study because they provide a stochastically driven damped harmonic oscillator kernel, and that is the SHO kernel. And the kernel function is shown here, and the PSD of the SHO kernel is shown here, determined by three parameters. The omega 0 are the frequency of the undamped oscillator, the Q is the quality factor, and S0 is proportional to the PSD at omega equals to omega 0. We use four parameters to build our GP kernel: the characteristic amplitude sigma, the timescale rho, and the damping timescale tau. These three parameters are alternative parameters for the PSD of the SHO kernel, and a noise jitter term in the GP regression, C jitter, to represent the white noise in the light curves. There's also a derived parameter Q equals to pi tau over rho, and it means the quality factor of the oscillator. Specifically, if Q equals to 1 over square root of 2, the PSD can simplify to this form, and this is similar to the Harvey-like function shown here. So this kernel function is suitable for us to study the granulation, and Bowman and Don Wallenstein studied the stochastic low-frequency variability of 30 OB stars, and also found that their Q values are really around this term. As for our results, they are confused by model distribution of Q at one peak around log Q equals to minus 1.5 and another at log Q equals to 0. Because the Q is essentially the quality factor, a larger Q means a significant variability or even a perfect periodic oscillation. We infer that these two peaks correspond to two different kinds of light curves. And that was the case. This figure shows two examples of light curves from these two peaks. For the larger Q values, the GP model reproduces the stochastic variability in the light curves well, but for the smaller Q values, the GP model can only capture a long-term trend. Indeed, the light curve shows here doesn't exhibit any significant variability like this. This makes sense because Q equals to pi tau over rho. A smaller Q means that a damping time scale is much shorter than the undamped period, resulting in a light curve like this. So we conclude that the right peak can really represent the granulation signal we are looking for, and we use a double Gaussian fitting on the kernel density estimation of this distribution and select the right peak. The plot of sigma over versus Q also shows this because selected source span a wide range of sigma, while the smaller Q clusters at lower sigma values. That is because the smaller Q means any deviation from the mean will immediately suppressed, resulting in the small sigma values. We also calculate the stellar parameters of our rare supergiant samples. Firstly, we established a relation between effective temperature and intrinsic color. The temperature is coming from an apogee survey, and then the luminosity, radius, mass, and surface gravity can calculate it through these formulas in turn. And that's our latest scaling relations in the SMC and LMC with the complete sample of rare supergiant stars. This figure shows granulation timescale rho versus stellar parameters. The outliers shown in transparent dots may be contaminations of other unknown type of stars, so we remove them from our analysis. But for the rest of the stars, there's well-defined scaling relations, and it may be a new way to infer the stellar parameters because they without spectra, but only the light curves. As for the amplitude, the trend is different because the bright end and the faint end seems to follow different slope. This may be because that there are some non-varying rare supergiant stars at the faint end of the RSG branch, as noted here by Yang et al. So we use a piecewise function to represent the scaling relation and to coincide with the luminosity mass loss rate relation, as noted by Costas and also by Wen et al. You can see her talk tomorrow morning for more details. And we also compare the difference between our Gaussian process regression and the PSD fitting shows here, and the blue line and the red lines shows the result from these two methods. And the comparison of the parameters are shown below. Actually, there's no significant advantages for PSD fitting over GP regression because, as I mentioned earlier, there are several issues in calculating PSD, and the deviation of the dispersion of the sigma seems smaller, and for the time scale, it seems larger because they are so difficult to measure. As the SMC and LMC covers a wide range of metallicity, so it is comparable for us to study the difference in these two galaxies, and we found that the amplitude and time scale of granulation increase with metallicity. And that is because the simulation shows that metal-rich stars have a larger granules due to their increased opacity, because the granule size is proportional to the pressure scale height HP, and the time scale tau and amplitude sigma also proportional to HP, and that's why they are increased with metallicity. As for the scaling relations, we found that the scaling relations of time scale rho seems close, but for the sigma, they are a little different. This may be because the granulation time scale may not be sensitive to the metallicity, but the amplitude are more affected. As for the effective temperature, they are different because at a given temperature, the amplitude and time scale in the SMC seems to larger than the LMC. This may be because that Levick and Messi shows that the spectral type of rare supergiant stars will become later with the increasing metallicity. It means at K2 to K3 for the SMC and M1 to M2 for the LMC. It means more significant difference in effective temperature in these two galaxies. So it also means an effect of metallicity on effective temperature is more significant than on the granulation, and that's why they are different. And this is my summary slide. We use Gaussian process regression and comma to model the granulation of rare supergiant stars, and we found a scaling relation, and also the granulation can be affected by metallicity. Here I show two papers related to this talk, and please cite. I will stop here. Thank you very much, and your questions are welcome.
Hi, great talk. I have two questions. The first one is, so you have OGLE data and ASAS-SN data, which are covering different bandpasses, do you see anything different in the same stars between those two different bandpasses?
Yeah, I didn't introduce it, but they are shown in my paper. Yeah, we found that they are slightly different in the amplitude. That
Right.
makes sense because they are in the different bands.
Yeah.
But for the time scale, they are almost the same. Yeah, because we compare the time scale derived from different bands, and they are all close to the one-to-one line.
Okay. And then this is related as well. So you talk a lot about the time scale, which I understand, but there's also, the amplitude of the Harvey model itself might have some information. Are you working on that at all? Do you have any say on
I don't understand.
the
amplitude?
The amplitude, say, on the top part of the Harvey model, right? So the amplitude of the left side rather than like the white noise on the right side. Do you have any does that hold any information for you guys?
Actually, we didn't give some more information for the PSD fitting because basically the JP model is conducted on their like curves and not involving the PSD. So this figure is just for comparison because the sigma is easy to measure because they are mainly corresponding to the plateau of the PSD shown here in the low frequency. And so I think that's why they are there's a smaller dispersion in the comparison of sigma, but the time scale is much more difficult to measure because they are corresponding to the knee of this Harvey function. So they are much more affected by the calculating PSD.
Okay, thank you.
You're welcome.